The diode is great for DC rectification, and that's what's coming up next. Greetings, the Astro 30 here yet again with another electronics fundamentals video, and today we're going to be looking at DC rectification using one of these, a diode, or a few of these actually. Not this specific diode, this is a signal diode. It's not actually really suited to rectifying AC voltage into DC because it has not very high of a current handling. For that you'd use diodes similar to 1N4004 to 1N4007 respectively. They have a forward voltage of 100 volt and 1 amp current capability. This is a 1N4148 and I'm not 100% sure of its current handling capability, but this was the only diode I had close to hand as a visual aid. Anyway, let's get into talking about DC rectification. Alright, for those that don't know what a diode symbol looks like on a schematic, it's usually drawn pretty much like that. And you have an anode and a cathode. Now looking at a regular diode, with this signal diode again, the anode is over here and the line usually represents the cathode, which is that line there. So this diode is now facing the same direction as the drawing on the schematic. So the first rectification circuit we're going to look at is the half-wave rectifier, which just uses a single silicon diode, such as a 1N4004. And the DC is formed over here at the cathode, it becomes a positive. And depending on what the voltage of this transformer is, say 15 volt, you're going to have 15 volt DC here. Now I will talk a little bit in a moment after I've gone through and discussed the three types of rectification that we're going to be talking about how we filter the AC, because when this is rectified we're going to have a signal that looks like that on an oscilloscope screen. You'll notice that there's dead spots here between the peaks. That's because the other half of the cycle is missing. Anyway, to remove ripple, to get an almost flat DC, you would put an electrolytic capacitor here, and that will in a sense give you an almost flat line, but you've got to choose the correct capacitance to achieve that. And also now the output voltage will be a lot higher. So to calculate what the DC voltage would be now, we take our AC voltage and multiply it by the square root of 2, which is 1.414 rounded, which gives us roughly 21 volt. So we'd expect to see 21 volt DC here on the output after using a capacitor to filter the DC signal. So let's look at this circuit on a breadboard without the capacitor installed for now, because we'll come to that later, and just see what waveform we get out on the output of a oscilloscope. Alright, so this is my setup. This is a half-wave rectifier, so a single silicon diode. I've got a 10k resistor here across the positive output and the negative ground, just as a load, so I'm not using the scope as a load. So it's got something to dump the current into. I've got the scope there in the background. I've got the multimeter on the DC volt range so we can measure the output voltage. And I've got my two transformers, which I'm only using one of them. Now there's exposed wiring here, so if you're following along at home, you're doing so at your own risk. Having exposed wiring around like this is exceedingly dangerous, and the chance of coming into contact with something, especially all these open terminals and stuff, is pretty high. So if you're doing something like what I'm doing, you're doing so at your own risk. The whole entire purpose of this video is just to demonstrate the different type of rectification circuits. Alright, we indeed do actually have power. Now currently we're getting 6.61 volt out, and as we can see on the scope output, even though it's moving around a bit, you can see that we've only got the positive peaks going through. The negative peaks are missing, and that's exactly what this rectification circuit does. Just carefully touch this resistor. It's not even hot, it's only dissipating around 4 milliamps. Now I'm across a 15 volt winding of that transformer. Why are we only getting 6.5 volt out? Well, that's because this is half wave rectification, and that's exactly what it does. We're only getting half the voltage because we're missing half the waveform, in a sense. And speaking of waveforms, that's exactly what I described would happen on the output of the oscilloscope. We're only seeing the positive going peaks of that waveform, and the negative going cycle, half cycle, is missing, which is exactly what we expect, even though the trace is moving across the screen because it's not triggered correctly. By the way, the scope is set to DC coupling. So that's half wave rectification, and apart from only getting half the voltage, the other disadvantage to this is it can't deliver a lot of current. So it's not suited to high current applications. It is okay to use on low current applications, and in a pinch that circuit will work just fine for low powered stuff. Anyway, let's now look at the next form of DC rectification. The full wave rectifier uses two silicon diodes joined at their cathode to form the positive, one end going to one end of a transformer, the other anode going to the other end of a transformer, and for this circuit to work you must have a center tapped transformer. So this is the center tap of the transformer, which forms our negative rail. Now the disadvantage of this circuit is you need to have a center tapped transformer for it to work. You can't just use it without a center tap. It just doesn't work. But the advantage is now our waveform on our oscilloscope screen will have no missing cycles because the other diode fills in the other peak that's missing, and so that's why it's called full wave, because all the peaks are accounted for. And this is assuming you don't have a filter cap. This is why it's drawn in a dotted line, because with that capacitor in, that would be almost a flat line, and the output voltage would be 21 volt. The other disadvantage to this is, even though this is a 30 volt center tap transformer, we're still only going to see 15 volt DC unfiltered and 21 volt DC filtered, because we've got 15 volt here between there and the center tap, and 15 volt here between the center tap and here. And because during each cycle the positive goes through this diode, so we get 15 volt that way, and the negative half cycle goes through this diode, still producing 15 volt to fill in the missing dead time blanks. So the only total output would be 15 volt, not 30. So keep that in mind. So now we'll test that one on a oscilloscope and see what our waveform looks like. And welcome to our second type of rectification circuit, the full wave rectifier. Now the setup's the same. I've still got the 10k load resistor here on the output. The two cathodes of each of these two diodes connect together to form the positive. It uses a center tap transformer where the center tap winding between the two 15 volt windings, it becomes our negative. One 15 volt winding goes to the anode of that diode, and the other 15 volt winding goes to the anode of that diode. Alright, and I'll plug it in there. And yeah, as we can see, we've got close to 15 volt. It's not quite 15 volt, that's only because probably of the diode drop of each of those diodes, which is 0.59 volt, something like that. And as we can see on the waveform, there are no missing peaks, there's no dead time. That is why it's called full wave. So on the positive half going cycle of the AC waveform, this diode is going to conduct and current is going to go flowing through that direction. And on the negative half going cycle, this diode will conduct conversely, allowing current to flow through this direction and returning via the center tap. And that is basically how the full wave rectifier works. And the advantages of this is that it can provide more current. The disadvantage is you need a center tap transformer, and it only produces half the voltage from said center tap transformer. However, this can be fixed by using the last form of rectification circuit, which we're going to look at now. And the final rectifier we're going to be talking about is the full bridge rectifier. Okay, Maddie, It's actually called a full wave bridge rectifier.
Full bridge rectifier.
Okay, Matty, calm down. Jeez, okay, it's a full bridge rectifier then. Anyway, jokes aside, you'll often see it represented as this diamond with diodes going through it. And we'll stick to that one for now, and I'll show you the other representations in just a moment. The advantage of this is with a 30 volt, even with center tap in there, with a 30 volt transformer, you would get the full voltage at its output of 30 volt DC without filtration and 42 volts with filtration. And you don't need a center tap, so that's its advantage. Plus, this particular rectifier can handle a lot more current than the two counterparts before it. And we're going to see the same exact signal on our oscilloscope here without a filter cap, because it's full wave. It still works the same way as the last circuit, and that's as basic as you need to understand about it without getting into a lot of engineering bullshit. So you can actually use the center tap to form a 0 volt and turn this power supply into a bipolar by adding two filter capacitors in series with each other. And now we have a 0 volt. However, if it's a 30 volt transformer, the thing is you're only going to see 21 volt here and 21 volt here, or 42 across the lot. So let's have a look at this without the capacitors on an oscilloscope, and then we'll get into choosing the correct capacitor. And before we continue on that, you'll often see the full bridge rectifier, I'm doing it now, represented on a schematic as either just a diamond with a diode symbol in the middle of it, to save drawing all the diodes, or you may see it drawn like this with the two cathodes on one side joined together forming positive, two anodes on the other forming the negative, and then each crossing over to the other winding of the transformer respectively to fill in the bridge. But it all represents the same thing at the end of the day.
Full bridge rectifier.
Now I'm doing it. And welcome to the full bridge rectifier. Anyway, the full wave bridge rectifier, hopefully I've got these diodes configured correctly. It now no longer needs a center tap, but you can include one if you want bipolar operation. Still got the same loading resistor of 10k there, oscilloscope and multimeter connected to the output there, just to measure what's coming out. Now I'm connected across the 15 volt winding again, so I expect to see close to 15 volt coming out. So hopefully nothing goes up with a bang. I'll plug it in. Well, 12.5, close enough. And as you can see on the output there, we've actually got all the peaks filled in. So isn't that interesting? Now it's time to look at filtration capacitors. So that waveform has a lot of ripple on it, and we want to smooth that out with a filter capacitor. So what is the right filter capacitor choice? Well, that is up to experimentation, so let's start experimenting. So with a capacitor connected the correct way around on the output, negative over here, positive over there, that's a 470 microfarad 63 volt cap, which is way overkill for what voltage I'm putting in. And take note of the multimeter display here when I plug it in at how much the voltage actually jumps up. See that? Now it is at 20 volt DC. Why? Because now with the filtration capacitor in there, we're using the square root of 2, which is 1.414, multiplied by the voltage coming out, which is 15. So it equals roughly 21 when all said and done. And if we look at the scope, the ripple is reduced, but it is kind of nasty looking still. So 470 microfarad is not going to fit the bill. So what do? Well, we increase the capacitance. Alright, now I've got a 1000 microfarad 63 volt cap in there, which again, the voltage is way overkill for the amount I'm putting in. Now the thing is, I don't know how good this scope is for measuring this sort of thing, because we're still picking up 50 millivolts of 50 hertz of mains hum from somewhere. There's something in this desk that's skewing the results. But we can see even with 1000 microfarad we're still getting a little bit of ripple. And we'll try a capacitor you really should be using, which is a 2200 microfarad, and this one's a 50 volt one, which is kind of a weird value. And plug it in, and now I'll plug the supply in. We've now got 20 volts still, and apart from that residual 50 hertz that it's picking up from somewhere in the room, I don't know where, there's almost next to no ripple, so we can negate that. That would actually be a nice smooth power supply now. The higher the capacitance, however, the better the results, and you can always put more of these capacitors in parallel to increase the capacitance. In amplifier design, 4700 microfarad is usually the norm, or 10,000 microfarad is usually the norm. Makes for great filtration. So yeah, that's a look at the various different types of DC rectification or AC rectification, whichever way you want to say it. Turning an AC voltage into a DC voltage, put it that way. So I hope you enjoyed this video. If you liked it, please remember to go down below and like, comment and subscribe as usual. And you can always follow me on Facebook, and you can become a Patreon for as little as $1 a month. The links are in the description as usual. Anyway, this is the Astro 30 saying see ya and be safe.